It's a like party day. You can go.
Okay, welcome everybody. Today we have Dr. Giorgio Valerin from Padova. It's a great pleasure for me to have him here because we do a lot of stuff together.
Likewise, thank you very much.
Giorgio started his research career in 2017, right, with the Professor Paola Marigo on with a thesis on progenitor scenarios for Type IIP Supernovae. Then he changed his mind. He said, why they are not interesting enough. So he moved to study low luminosity Type II supernovae and intermediate-luminosity red transients. He will tell us later what they are exactly. To explore their connection with Electron-Capture supernovae. And this is more or less what he did during the rest of his career. Now he's working for the Sonovic Shooter instrumental collaboration, which is a project led by INAF, by the PI is Sergio Campana. And his work is focused mostly on extragalactic transients and interacting transients. He also played a major role, I would say, in the recent paper on the antisocial supernova, which is famous last week, had a lot of attention. Okay, Giorgio, you have 45 minutes, right? Okay.
Right. Thank you very much. Thank you, Leonardo, for the introduction. Thank you, everyone, for being here. It's a pleasure. So today I will tell you about electron-capture supernovae, and we'll try to answer the question, are we actually observing some electron-capture supernovae? There is M51 on the background, which is wonderful. Later, you will see why. Spoiler, I was just lucky that one of the transients I studied was in M51. Very photogenic galaxy. So first, let's rewind a little bit and see what is an electron-capture supernova. Starting from a stellar evolution point of view, we have to remember that stars in the range of masses between 8 and 12 solar masses present a rather challenging evolution because they ignite carbon burning in their core and they undergo thermal pulses, just like HB stars, earning the name of super HB stars often. And here is a sketch of how a super HB star would look, so classic onion structure. But then the final fate of such stars depends heavily on some factors that are often difficult to model, such as stellar mass loss and the core growth, which depends on overshooting and convection, again, things that are difficult to model. So on this figure here, with the on the y-axis, you see the metallicity of the progenitor star, and on the x-axis, you see the initial mass. And so you see different shaded region represent different fates for the star. So in case the mass loss is very efficient, super HB stars can end their lives as oxygen and neon and magnesium white dwarfs. So the collapse is stopped by the electron degeneracy pressure. On the other hand, if you have very efficient core growth, overcoming the mass loss, then you have that the star will just undergo all the nuclear burning cycles and then will end its life as a supernova, as a core collapse supernova. I would say a standard core collapse supernova because this core that is collapsing is made of iron. However, there is a third possibility. When you have just enough mass loss and just enough core growth, you have that the star will collapse, ending its life as a supernova. But the core is not an iron core, but an oxygen neon magnesium core. Therefore, it's a slightly different kind of explosion. It's not exactly an iron core collapse. Now, this is exactly what is called an electron-capture supernova, because the collapse of the core is triggered by electron captures on neon and magnesium nuclei. Okay, so this channel describes the single star channel, where the star is isolated. And in this case, we expect the stars to retain quite a lot of their hydrogen envelope. Therefore, the ensuing supernova should show signs of hydrogen, like a type 2 or a type 2n supernova, so interacting supernova. There is also the possibility of having a binary channel in which interactions and stripping might play a role, and therefore you introduce other complicated parameters. But we will focus mostly on the single star channel and not on the binary one in this presentation. Now, for the electron-capture supernovae, we have some theoretical expectations. They are expected to have low velocities of the ejecta compared to the more classical supernovae, about an order of magnitude less energetic. At the same time, they should synthesize less nickel against about an order of magnitude less than what is typically synthesized. And finally, as we described, the progenitor star should be a super HB star, or at least compatible with the range of masses for a super HB star. Now the question is, are we observing something like this? Do we know some transients that fulfill these three conditions? So let's consider this graph. On the y-axis, you have peak luminosity of a transient, and on the x-axis, you have its evolutionary timescale. Now, the shaded regions show where the classical transients tend to cluster. So we have thermonuclear supernovae, type 1a. We have core collapse supernovae, all the other explosions. And then you have classical novae, which are, of course, very different from supernovae because they are much, much fainter. They are not actual explosions. And this is the standard classification scheme for supernovae. So does it have silicon? Then it's a type 1a, or better, is silicon dominating the spectra? Helium, discerning type 1b or c, and then hydrogen, type 2. Okay, where are we looking to try and find some electron-capture supernovae? Well, we know they are supposed to be faint, so we would probably start on the lower end of core collapse supernovae. Thermonuclear supernovae, something completely different. The subtype that is probably the most similar to the expectation for electron-capture supernovae are type 2p supernovae. The P stands for plateau, and in fact, their light curves, so these have luminosity against days. The light curves of type 2p supernovae show a period of almost constant luminosity for a few months before dropping and then settling on an exponential decline, linear in magnitudes, which is powered by the decay of nickel 56. Now, it is rather accepted that the progenitor stars of type 2p supernovae are red supergiants, and there has been a seminal study by Smart done on this. But as you can see, there are many events that span quite a large luminosity range. So is it possible that maybe on the lower end of these scattered events, some super HB stars are exploding and we are classifying them as type 2p supernovae? It's possible. Let's consider this. So this was from a work I have done. Here again, you see light curves of type 2p supernovae. You can see again the first phase where the luminosity is almost constant before the drop. And one thing that you can get from the light curve is if you consider the late time linear decline in magnitude, you can compare the luminosity with the well-studied supernova 1987A, for which the nickel mass powering the light curve has been fixed and calculated very precisely. So with a simple ratio between the luminosity observed and the luminosity of 1987A at the same phase, you can have an estimation of the nickel mass synthesized during the explosion. And here, if you plot the luminosity during the plateau of the supernovae against the nickel mass synthesized, you will see there is quite a strong correlation between these two parameters. So most luminous events will have most nickel 56 synthesized. But on the other hand, you have some events that are faint, and so we expect with low explosion energy, and the synthesized quite significantly less nickel in the range that is expected for electron-capture supernovae. So this is promising. From the spectra, here are some examples of spectra of type IIP supernovae. We can infer and measure the expansion velocity of the ejecta. Here is a sketch to remind you the formation of the so-called P Cygni profile. So if the observer is here, the intervening material between us and the photosphere will cause an absorption. But then, of course, there is the emission by all the other material. And at the end point is this sort of, oh, well, it's a P Cygni profile. So from the minimum of the P Cygni, we often measure the velocity of the expanding material. This is very useful because from the luminosity, from the expansion velocity, and finally from the temperature, which is typically the recombination temperature of hydrogen, we can perform some hydrodynamical modeling. These have been performed by the team in Catania, Maria Letizia Pumo. They have developed a code specifically to fit this sort of observations. And the results, well, for some events, you have results that are perfectly in line with red supergiants, masses above 15 solar masses. But for the least luminous events, then we start having progenitor masses that are estimated to be around 10 solar masses. Again, this seems to be quite promising. So if we look at what we have, these are the parameters for this specific fit. Are low luminosity type IIP good candidates for being electron-capture supernovae? Well, they fit the bill for the little nickel that has been synthesized. They are definitely low energetic because the expansion velocities are lower. The progenitor stars, well, they are in the range of masses that is correct, but are we sure that they are super AGB and not maybe red supergiants that are very low mass? That is quite difficult to determine for certain without the direct detections. Now, this could be the picture that we have. So in this graph, we have the luminosity against the ratio between energy and mass ejected. But this is just to show, again, that there is a correlation between these parameters. So you have type IIPs that are very energetic, very bright. This we have basically no doubt that they come from red supergiant type of progenitors. While the lower end of this distribution maybe come from super AGB progenitor. There has been a recent study, very interesting, from a sample of over 300 type IIP supernovae. Here you see the binning in magnitude and the relative frequency. So what they see, they managed to calculate the rates of type IIP supernovae and low luminosity type IIP supernovae. And they compare this rate with the expected theoretical amount of stars in the range of 8 to 12 solar masses that are expected to explode. And they see that there is almost a factor of 10 between low luminosity type IIP supernovae and stars between 8 and 12 solar masses. So where are the missing explosions? We should see other transients that explode in this range of masses. So back to the drawing board. Where are we looking to find such transients? Well, first of all, let's consider that the situation, as always, is more complicated than initially thought. So this is the same graph, but as you can see, many more transients have been added because in recent years, more surveys have been carried out. They have found a number of peculiar transients that fill regions that were previously apparently empty. And even the classification scheme has become challenging. It's not a very easy flow chart to follow. Even question marks are thrown around sometimes because, of course, life is complicated, nature is complicated. So in particular, in the range of luminosities between the standard core collapse supernovae and the classical novae, there is what is often referred to as the gap, meaning the luminosity gap. And here you often find what are called supernova imposters. So transients that may look like supernovae, but they are not necessarily supernovae. I want to quickly show you a couple of examples just to show you that it's not easy to just pinpoint exactly the kind of transient you're looking for electron capture supernovae. One example are luminous blue variables eruptions, very massive stars. They undergo hectic changes in luminosity. Here is a light curve of one of these transients. You can see the variations are very difficult to predict. And the reason why they are called imposters is because their spectra resemble very much those of actual supernovae, supernovae type IIN, so supernovae that have interaction with circumstellar material. And originally, these were the supernova imposters. And this is a beautiful image of the homunculus nebula, Eta Carinae, which indeed has undergone a similar sort of variability. Another example that I find fascinating are luminous red novae. This is an actual image of a luminous red nova, galactic. So that's why we have such beautiful image, a V838 Monocerotis. And this is the light curve of another event, the V1309 Scorpii. Now, what catches the eye, of course, is this quite impressive peak, which is the event itself. But what tells us what these events actually are is what happens before. So the variability before the very big outburst actually shows to have a period, quite well-defined period. So they also observe this period diminishing with time quite impressively. So the interpretation has been that these are binary systems, actually non-degenerate stars, so it could be main sequence stars, that are orbiting each other, and the system is shrinking, losing momentum. And then at some point, they enter a common envelope phase, which shields the system from our view, and that's why the luminosity drops. And then the two stars actually merge, and that's the event we are seeing. Now, the interesting thing is that the star is expected to survive, the merged star. This one is the star after the event, so it has clearly survived. It's not an actual explosion. And these are the light curves. They can be rather messy. They can show double peaks. But again, the spectra, they can be confused for a supernova at first because they, again, have these very narrow lines. So again, supernova imposters. By studying the progenitors of these objects, we have seen there is a clear correlation between the mass of the progenitor and the luminosity of the event, which is quite interesting. This is not necessary for this presentation, but I wanted to tell you because I found it quite interesting. So you see, the most massive systems merging have the brightest outbursts of this kind of objects. Enough of luminous red novae. Now, these are the targets that we are interested in, which is intermediate luminosity red transients. Now, you can see the object is this tiny dot there because we have passed from studying galactic transients to studying extragalactic transients. Now, this is the closest we have ever observed because it's just a 2 megaparsec. Everything else that we've studied is definitely farther than that. Now, intermediate luminosity red transients, again, belong in the gap of luminosity between standard supernovae and classical novae. Their light curves are very similar to supernovae, actually. They have a single peak. The late time decline appears to be very linear, similar to the nickel decay. And even the rates, there are some differences in estimates, but around a few percent, 1 to 8% of the total core collapse events, which is actually exactly what you would expect for electron capture supernovae. So another interesting point in favor of the interpretation of these events as electron capture supernovae. We have two very well, oh, sorry, I didn't tell you, but up to now we have studied less than 20 of these events, so we don't have massive statistics. So we have two events for which the progenitors were detected surely, and these are the progenitor detections. They are quite similar, of course, between each other. And they have been interpreted as extreme AGB stars. If you put them in a color magnitude diagram, they are clustered together with what are called extreme AGB stars. And there is quite a consensus that they should be stars between 8 to 12 solar masses surrounded by a lot of dust. Absolutely invisible in the optical, but very bright in the mid-infrared. The spectra of the events look something like this, which is not exciting, I am aware. Very narrow lines, mostly dominated by hydrogen and calcium features, so low ionization, low temperature, low energy. From the full width at Al maximum, you can tell that the material that we see is not moving faster than 1,000 kilometers per second. And the evolution is very slow. In few months, they barely evolve. This is the most beautiful spectrum we have for such objects because it has been taken with VLT plus UVES, so very high resolution, quite good signal to noise. But what I wanted to show you was a close-up from this spectrum of just few calcium lines. So the blue one is calcium second H. The green one is the calcium second forbidden line, one of the two of the doublet. And the red one is the calcium from the calcium forbidden triplet. Now the shape is very interesting because the green line shows this very asymmetric profile, which is has actually been explained from Huang and Chevalier as the effect of a wind and the plus electron scattering. So what we can tell from this sort of spectrum is that there is a wind emitting the calcium second forbidden line, and at the same time absorbing the continuum and the lines coming from underneath. Because if you look at the red line, you can see that there is an absorption that is exactly mirrored as the emission line, just of course in absorption instead of in emission. So there is some intervening material that is this slow wind, about 30 kilometers per second, that is between us and the CSN, the circumstellar material that is producing the broader line. I say broader, but actually in supernova terms, they are very slow. Now, regarding the light curves of these objects, bolometric light curves, so something that I have done is to take the spectral energy distribution of these objects for more than 1 year, from the optical to the mid-infrared. And when you start integrating these bands, actually you see that at late times, the decline is not exactly what you would expect for the nickel, which are shown as straight dotted lines. And one reason why, a possible reason why this is so, is that the material is hitting the dust surrounding the transient, and the shocks are providing additional energy. This is okay. M51. You have seen the transient now that is giving the background of the first image. So we were lucky that JWST has observed one of these objects over 5 years after its eruption/explosion. And the spectral energy distribution observed by JWST has been puzzling, very difficult to reproduce with simple black bodies, even when you try to account for dust. So possibly there are polycyclic aromatic hydrocarbons that are producing lines that make this very jagged profile. But if you just care about the luminosity, then it's rather easy. You just integrate with the trapezoid rule, and that's it. So you can see it even more clearly now, even after 2,000 days. Well, this would be the expected decline rate for the nickel. You can see there are several orders of magnitude of difference between what we observe and what we would see if there was only nickel there. But we can do even better than that. And this is probably the takeaway. If you have not found anything interesting so far, I hope you will find this interesting. So Spitzer monitoring of several years of 3 of these transients, the closest one. So 2, 5, and 8 megaparsec, the 3 closest we have ever observed. Here you can see the images. So the progenitor, 3 years after the event, and then 7 years after the event, and 11 years after the event. 11 years after the event, we were not able to detect the transient anymore. And in this case, these are again light curves, so luminosity versus time. These objects, these figures regard the blue object evolution. But we can see that a similar trend is true for the other two objects observed. The horizontal line shows the luminosity of the progenitor, because in this case, we have observed the progenitor for all three objects. And all three objects, if you wait long enough, which is few years, so you have to be patient, but all three objects have shown to go below the luminosity of the progenitor quite substantially. Now, if this was the optical, of course, you can argue that it's just due to dust occultation, of course, but this is the mid-infrared, so it is quite difficult to occult from there. And so these are actually points that suggest that these events might be terminal, that the progenitor is no longer there, or at the very least has been altered significantly. So this is a good point in favor of these objects actually being supernovae, because the question is, what are these beasts? What are intermediate luminosity red transients? Let's go very quickly through the possibilities. So they might be stellar eruptions, maybe. Well, originally someone suggested that they might be. The problem is that stellar eruptions typically come from much larger stars, not 8 to 12 solar masses progenitor, so you would have to come up with other mechanisms to propel this sort of eruptions. The kinetic energy would be on the mark, but the terminal nature, well, stellar eruptions do not really have that, so we would exclude that. Fallback supernovae, well, fallback supernovae would be good for the kinetic energy and the terminal nature of the event, but again, we would expect fallback supernovae from much larger progenitors. Stellar mergers, the luminous red novae that we have discussed before, well, in this case, you can have stellar mergers with objects of those kind of masses, and the kinetic energy would be perfect. But again, the star is expected to survive in these cases, and so we don't believe they are stellar mergers. Electron-Capture supernovae, maybe. I mean, the progenitors seem to be exactly what we're looking for. And if the light curves tell us that the nature is terminal, then that's a significantly, that's a good point, let's say. The problem is the kinetic energy, because the kinetic energy that we observe is too low, conversely to what is often found, that maybe the kinetic energy is too high to be an electron-capture supernova, but no. So what we would need to have is that there must be fast ejecta, faster than what we observe, underneath the circumstellar medium. This is not impossible, because it is often observed in Type IIN supernovae, the interacting supernova with circumstellar medium. We know that they have fast ejecta, but we only see what is on top of this ejecta, which is slower moving material. Although up to now, we have not had the chance to actually make sure if this is the case for these objects. So where do we go from here? Well, of course, monitoring very late time with instruments like the JWST seems to be a very good idea. Making sure that the objects are really disappearing. Put the best constraints that we can, and then you can perform some modeling, for example, with Dusty, to make sure that there is no star underneath there, no matter how much mass of Dusty you put on top. So this is surely something that should be done. And also, another thing that can be worked on are the rates, because as I was telling you, we have less than 20 events up to now. Of course, the statistics is not great, but something that might change this is LSST. So one thing that we are working on is to build the templates of these objects based on their light curves. So you can use these templates as a filter to select the objects that look similar in the LSST survey. And maybe we can build a sample that is much larger. And, you know, statistic helps. For example, for the determination of the rays, that, as I was telling you before, is quite uncertain. And of course, let's not forget the spectroscopic part, because the sonographic shooter, with which I'm working with right now, well, we will have a facility specifically designed to observe transients. And it can answer some very important questions. For example, as I was mentioning, are there fast ejecta underneath the circumstellar medium of red transients? So very late observations would be definitely useful here. And to go back on the low luminosity Type IIP supernovae, which are the products of the nucleosynthesis, because you see another expectation for electron capture supernovae is that they would produce significantly more nickel, for example, compared to iron with respect to standard iron core collapse events. So if we are able to observe a low luminosity Type IIP supernova at very late phases with SOX, then we could put constraints on the nucleosynthesis itself. And this is what I have prepared. I have tried to be as concise as possible. There are a few things that I have cut, and so if we do have time, I can show you very quickly. But in the meanwhile, thank you very much for listening, and thank you.
Okay, thank you, Giorgio. Are there questions?
So, are you here tomorrow?
Yes, I am here.
No. Just a quick question. We have shown this range of transients for the progenitor area as well. This is very large.
Yes, I agree.
I mean, if you put that in a statistical sampling, no, you should, and considering that to be progenitor at mass, according to this, 12 to 20, let's say, more. That means, and considering that the mass function is very steep power law, so you should expect a significant fraction of the core collapse that are electron capture. So this is definitely too much. Actually, according to extant model, if you look at the latest investigation of these stars of intermediate mass, no, above 8, 7, 8, so amazing. You may see that even if you do not consider any overshoot during the core hydrogen burning, a star with 9.5, 9.6 solar mass in solar metallicity really need neon. So skip the super HGP and burn everything up to the higher peaks. So in that case, it will appear as a plateau one. So this range is probably smaller. So the question is, how many of the supernovae you expect? Because it seems that till now there is no clear in the smoking gun to identify this supernova from observation, directly from observation. So the point is, statistically, we may say exactly how many you expect. 1 over 100, 1 over 1,000 core collapse, 1 over, I don't know.
Yeah.
So how many?
First of all, very good point. Indeed, I thought about mentioning it in the beginning that 8 to 12 solar masses is a very large range, but it can be seen here from this study from the ELRT. The actual shaded area corresponding to electron capture is very small. Like if you look at basically zero metallicity, it's not even half a solar mass. I adopted a range of masses that is often mentioned, maybe wrongfully so. I guess one of the reasons why the range is kept uncertain is because this kind of modeling, at the very least, has quite some dependence on the metallicity. And so as the metallicity changes, this strip of perfect masses changes. And so even for this model here, you can have stars that go from 8.2 to 9.5 maybe. So yes, I do agree. 8 to 12, way too much. Surely not all the stars from 8 to 12 solar masses will undergo an electron capture induced core collapse. And I guess this is kind of the problem, right? Because if we are not sure about the range of masses that will actually lead, like, of course, we can try to have the best modeling possible, but depending on the model that we adopted, then I guess we can have an estimate. To my knowledge right now, the best estimates that we have for electron capture is few percents of the total core collapse events. Few percents meaning 5, 8%.
So 1 per year, at least, no?
Even more.
More.
And yeah,
One year, 100, at least 100.
it depends on the distance.
Yes,
Yeah,
that's
it depends.
These days they are out there, so.
200 megaparsec.
no, how many we observed. We discovered. Okay, but with LSSD probably this will increase.
Yes, the way we did the templates.
So related to these, wireless SSDs, will it be Roman you're rushing for this?
Well, I guess LSSD has, of course, quite a deep limiting magnitude. Maybe one concern with LSSD could be the cadence of observations.
Yeah, and Roman has an infrared and it's deep, right?
I guess that's a good idea. One problem with that is that the building of the templates would require very good light curves in the near infrared, which we have for significantly less objects. I would say 5 maybe out of the 15 to 20, while yeah, so building a template can be challenging in that sense. But it is a good idea. And in the future, as the sample grows, it's probably the way to go. The way to go, yeah. Because I agree, these transients are red by definition. It's in their name. So looking in the infrared is a great idea. Let me give you an example, because it's something I wanted to mention and I was afraid I didn't have time, but I guess I have a little bit. Okay, so there has been this case, supernova 2018 ZD. So it exploded a few years ago, and it was quite a hit, because there has been a paper in Nature Astronomy claiming that this was indeed an electron capture supernova. Based on few indications, for example, there was signs of circumstellar interaction in the early phases, although that is no smoking gun, because we know very well that there are many standard events that present CSM interaction in the beginning, in the first phases. But one of the points was that the nickel mass produced was just in range of being an electron capture, and also that the energetics were relatively low. One issue with this was that the distance adopted was 9.8 megaparsec. The problem is that in the literature, most distances for the host galaxy were closer to 15 megaparsec. So of course, the distance was quite a big point here. The paper itself had an independent estimate based on the tip of the red giant branch, if I'm not mistaken, but I should double check this, but they had an independent way to measure the distance, and they adopted their 9.8 megaparsec measures. So this is the same graph that we discussed before, peak magnitude against the logarithm of nickel mass synthesized, and you can see that adopting the two different distances, you have quite different events, because while in the case of about 10 megaparsec of distance, you have, sure, it's barely in range of the upper limit for the electron capture expectations, which is around 10 to the minus 2 solar masses of nickel synthesized, which would be here. While if you adopt the most commonly found distance in the literature, then you have an event that is much closer to the standard events, which we would associate with the red supergiants.
They are both on the border, one side and the other, more or less.
Yes, that is true. Although,
if you put error bars, probably they are the same value.
the error bars are the shaded area surrounding I guess this is the logarithm, so it can squeeze somehow. But even the peak magnitude, although again,
It depends on distance, okay,
absolutely.
but they are very close to the border.
So theoretically distance for an object like this one will be big.
what I wanted to say is that we were lucky. Last year, there has been another supernova, very, very close. No, not Type 1H, Type 2P. And we have observed, so this is the light curve of this object. We were able to obtain several spectra, and so we measured the expansion velocity from the scandium lines, and they are these pink stars. So actually, remarkably low velocity, this new 2024 ABFL, a remarkably low velocity compared to the rest of the sample of explosions that are already subenergetic, so impressive. But what is interesting here is that we can use a relation that has been calibrated specifically for Type IIP supernovae. The physics behind it is basically the expanding photosphere method. So the velocity is used to estimate the radius of the source. And therefore, using the observed apparent magnitude, you can infer the distance modulus. So this is the equation that was calibrated by Rodriguez. So you can see that using the velocity at the photosphere and the observed magnitude, these are some parameters that are calibrated by them, you can obtain the measure of the distance modulus. So this is a different way of getting the distance. I have adopted this specifically for the I, J, and H filters, which were said to be the most reliable for this specific kind of estimate. And what I find is 15.6 megaparsec, which, as you can see, is remarkably in line with other independent estimates that are found in the literature. Definitely not with the 9.8 megaparsec that have been used. So I would significantly favor the point with a larger distance. And therefore, I would say that 2018 ZD is not a great electron capture supernova candidate. But again, this whole discussion was to show you the challenges that this sort of hunt carries with it. Because even when you have, let's say, there are several things to take into account. Okay.
Questions?
Oh, please.
So another question concerning the possible observable to intercheck. The core mass of the progenitor actually basically depends on the nuclear physics uncertainty. So I think that it's quite good known. Invariant with the total mass that is depends on the shooting. So, and according to standard models, the core mass should be in between 1.1 and 1.3 solar masses, more or less. Below, they do not emit the carbon. Above, they emit neon and so on. So this, and since to activate the electron capture, the electron should be cancelled relativistic. So they should grow, the core should grow approaching the Chandrasekhar mass during the super-Elgin phase. So it's not negligible part of the super-Elgin should be completed until this condition of relativistic electron is attained. And so this means that also the mass of the envelope is could be strongly reduced in this system. So yes, I expected that at the moment of the explosion, the envelope mass should be significantly smaller than normal 2P supernovae. So the question is, are there some way to measure the mass of the envelope, to estimate the mass of the envelope? I mean, the expansion rates, it's complicated. In type 2, it's above 100 days now. Typical type 2B is 100 days.
I guess
But the shorter plateau may be also the consequence of the lower power of the supernova. No? The fact that the supernova is fainter, this means that the expansion rate is slower.
Well, in this specific, so the closest thing that comes to mind right now is the hydrodynamical modeling that has been done, for example, by Letizia Pumo, which again, we try to fit the luminosity, the expansion velocity, and the temperature of these objects. These, of course, put some constraints on the ejected mass without differentiating envelope and core. So it is a bulk,
Yeah,
whatever
if
is
a
true.
reasonable assumption about the core mass.
That can be done. That surely can be done. Then I know there are also some complications about the nickel mixing. For example, this is a good example of that. You see that the very end of the plateau is not well reproduced by the model. It is the observations are brighter compared to the expectations of the model. This is not true, for example, for the case of 2020-60. And one way that this was explained was through nickel mixing. Like if the nickel mixing is very efficient, then it is possible that this plateau is sustained for a longer time compared to other events. So this to say, I think the parameters at play are a lot. So pinpointing exactly the mass of the envelope, for example, seems to be difficult. And this is for the case of type IIP. For the case of red transients, there is an additional complication, which is the interaction with circumstellar medium. In fact, their light curves are definitely less standardized in a sense. Sure, they do look like supernovae because they have a single peak, but there are some events that are definitely slower evolving and some events that are definitely faster than others. Maybe it can be seen much better from here. Okay, you can see, for example, the two brightest examples. One has a rather slow evolution, and the other almost seems like a type Ia. And this is possibly due to interaction with circumstellar medium. So again, those are other parameters that are introduced that can change the shape of the light curve, depend on CSM itself. So again, the mass loss history of the star comes into play. Sadly, I would say that here we have even less control than in the case of type IIP. So maybe the case of type IIP can be a good starting point for this sort of reasoning.
Challenging.
I agree.
Question, if I can.
Just a comment. The idea is that if you have the the ejector for the very fixed ball, we have the mass of course. And the other comment is that the mixing of radioactive get to a model, of course.
Yeah, but these are super HD stars, so they probably have the envelope is enriched with the heavy helium, and so the opacity is larger than so you may have a situation.
Okay. I agree with you. It's not easy to model. But then once again, you can try to fix the uncertainties due to that. And the other is a comment concerning the mixing of legal 56. It dates back to the model, to understand back to model. It was demonstrated, it was not there. So I mean, involving the could explain, but it seems not really very realistic. Let me say.
Fair, and it can be, and then there is a need to find another reason.
I think I know that one of the first slides, actually, the very first ones. Okay, keep quick. Okay, this one. What is the driving that really drives these three possible scenarios?
Well, again, if we have very efficient mass loss, maybe during the thermal pulses.
Yeah, that's the question. I mean, what does it drive?
Yes. So, for example, metallicity can play a very important role, as in stellar winds. For example, you have a more efficient mass loss and therefore the star is strict.
Therefore, you expect the dependence with the star formation. Because if
Well, also,
Yeah.
yes, since the metallicity, and you can also see it from the estimated range.
this means that you find this, you should find, okay, you have a statistically poor sample. But then, once you have a richer sample, you expect that a residual dependence with the environment.
Oh, well, yeah, I guess the theory tells us so.
Okay. And then the other question is, if you go to the few couple of next slides, probably. Yeah, there's a mass, there's a comment that was here, you go after. Yes, this one, go back.
See.
What does it call this A12, the estimate of the,
Okay, so
where does it come from?
these are all numbers that have been reported by the article that's et al. So to obtain this this rate, they first assumed the salpeter initial mass function. They assumed it. And then they took the total. Why not?
It's an assumption.
And then they took the total.
Because we know that it's not, we use now. I think it is 2025, it's not 1988.
So what do you prefer?
I don't know, we use more. I disagree. Something, I mean, something that less as peaky as the salpeters, the people, no.
Which one? Cooper.
Yeah, I mean,
But it's considered that.
well, then for
It's
the,
about.
yeah, I mean, okay, now these are the
Yes,
mass
but
functions.
the mass.
Okay, whatever.
It depends on what range you are considering.
Yeah. So that's the normalization factor, I mean, whatever. No, it's not. So is that the assumption?
Yes,
So
yes,
it's not
yes.
gonna work. I'm complaining about that. Where does it come from? It's basically, it's an integration of the empirical.
Integration of the initial mass function within A12, and then they took the measured rates of core collapse events, I think from Lee 2011. Okay.
So they are ones are one factor of that.
Of course, if they are single star, they evolve only as single star. Because most of these massive stars are in binary. So during the AGB, the super AGB, the envelope expand a lot.
And so they have
700 or solar masses. And so you may feel the rush up and transfer mass and go, and since the mass transfer is very high, you have common envelope and you will solve the envelope. So if you introduce variability there, probably these numbers are much smaller.
This is one of the explanation for the mass loss we were asking before.
Okay.
Other questions on that?
Questions of life. Very difficult. Okay. Okay.
That's again.
Thank you very much.
Next seminar is in 2-3 weeks, and we have Maria Pia Di Maus in 3 weeks. Yes, the end of this month. Ciao, thanks everybody.
Thank you.
Senti, la